Hello, my name is Cedric De Los Reyes, and today I'll be starting our final project presentation, Traffic Sign Detection with YOLO version 11. Here's a quick overview of what I'll be going over. First off, it will be going over vision and goal, the technical stuff such as YOLO and mean average precision, and then the basics of training a model, such as pre-processing it to make sure we know what we're working with, training and testing, and validating our model. And then we'll go over future work and improvements that we could work on, as well as limitations that we had, and then finally our references. So first off, I'll start with our vision, or why we wanted to do this project. The reason why we wanted to do this project is there's been some incidents regarding self-driving cars endangering drivers and pedestrians alike. One incident that I'd like to mention is that there was a cruise car that dragged a man down a street, which is obviously very bad, legal and fatal consequences. As a result of that, there have been a lot of concerns regarding the safety of these cars on Reddit, Twitter, and Instagram because with that incident, there has also been instances of the cars being faulty or not moving or getting stuck. So, in order to improve the public view of these cars, what we want to do is start off with the basics, improving the street sign detection system for these cars. So, in order to do that, what we want to do is we want to keep West Campus and UT Austin safe, but in order to do that, we need to have these vehicles correctly identify street signs using a training set and a test set and a validation set of static images, just still images with the YOLO algorithm. So you may be asking, what is YOLO? At a baseline, it pretty much is a computer vision algorithm that detects and classifies objects around a border, a probability, and identifying the object. One such example, even though it's wrong because we didn't train the model at that time just as a baseline, is that traffic light point 52 and it appears to be a crossing sign, which is obviously wrong, right? But that's the baseline. That's pretty much what an example looks like. So as far as the what it's comprised of or the architecture of YOLOv11, it's just one neural network. And the fun thing about it is that it beats other algorithms such as R-CNN in terms of accuracy and runtime. Now, for the version used, it's the 11th version, and for parameter tuning, there's a neat part about this where you have random and grid search CV, but you don't need to use those for YOLOv11. It just automatically does it for you based on what you're feeding it and how much you're feeding it.
So to measure the performance of our YOLO model, we use MAP or mean average precision. Basically, it's the average of the average precision scores across all the different classes in our data set. So that can include stop signs, their speed limits, etc. The MAP score will range from 0 to 1, with the scores closer to 1 being more accurate. And to go more into detail, we outline the steps here. So the first step would be to find the precision and recall for each class. Precision being the ratio of correct detections to all the detections overall, and recall being the ratio of correct predictions to all the actual objects. To find it, it would require finding the intersection over union, which is just how well the predicted boundary box overlapped the ground truth box, which we can calculate by, we can see in our previous slide, um, dividing the overlap of the area by the area of union across the boxes. And from this, we can form the precision recall curve graph, as you can see here, with the x-axis being recall and y-axis being precision. And the area under the curve we can use to calculate the average precision for each class. And finally, we just average all those scores across all the classes to get our final map score.
So before actually training the model, we needed to do some data pre-processing. And within the data pre-processing, the dataset that we originally used only had speed limit signs. So we decided to add a variety of signs to increase precision of the model. These signs included stop signs, warning signs, and parking signs, as you can see from the images below. We used a dataset of over 8,000 images to train and test and validate the YOLO model. And to start, we randomly displayed 18 images to essentially identify what type of images that we were working with. And additionally, we had some slight obfuscations made within the images to further test the YOLO model, with there being like angle adjustments, tilts, watermarks, blurs, as well as pixel changes and pixel discoloration. These images also came in different shapes and sizes, and we used a pre-trained YOLOv11 model to essentially train on this dataset. We additionally tried to see what type of images the dataset had, as well as how many of there are of each, and we created a little graph for you to represent essentially the names of each signs that we had and the amount that they were carrying within our dataset. So this bumps, of course, would be above 200, parking signs above 100, etc., all the way to however many signs that we had.
All right, on to me. Hi, my name is Tanner, and I'm going to start by going over the YOLO version 11 hyperparameter specifics. So, as you know already, we've decided to train the model on YOLO version 11. Specifically, we decided to train on the nano version instead of the medium or large or extra large versions, and this is because the larger versions are known for taking up more computing power and more memory, and overall it's already pretty hard on the system if you don't have good specs. So and as you might already know, when we were training on 7,000 8,000 images, when we tried to train over 10,000, the computer was crashing. So the nano version overall, it's just more efficient for a smaller use case just for our own computers. But as you can see here, after training on the YOLO model, we used its own automatic optimizer to find the specific parameters to use. And as you can see down here, it decided to use an AtomW optimization algorithm, and the learning rate came out to 0.00037 with an initial learning rate of 0.01, and then a momentum of 0.937 and a weight decay of 0.005. So as you can see, it started off with a relatively big-ish learning rate, and as it went on, it started slowing down as it reached the end of the 100 epochs and started to find the most optimal weights. Moving on, this is the training overview. So, like I said, we've trained the model on over 100 epochs. This is to ensure that we did not underfit the data. And also, the more epochs we go over, the more they're able to adjust the hyperparameters and reach the best weights. So after we decided on the best weights, after the 100 epochs, we ran the model, and these were the results that we got on the validation test set using the MAP 50 precision metric that we've already gone over. As you can see down here, the average MAP 50 score was a 0.97 for the 23 different classes. And as you can see here, for the different classes, we had as little as maybe like 23 validation images, but up to 130 validation images. So this test set could definitely benefit from more images, but like I said, with the limited computing power, we were only able to do about 8,000 images for this training. And this picture down here also shows the last 20 epochs. So by epoch 91, we were already reaching 0.96, and we got that to 0.973. And lastly, I'm going to be going over the dataset augmentation. Like I've been telling you, we ran this on about 7.8K images, around 8,000 images. We started on an original training set that was about 3,000 images. But we used some augmentation techniques to improve the model accuracy so that it had more images to train off of. So we did some image rotation, about -15 to +15 degrees. We did some exposure adjustment, so we turned the exposure from from 0% up to a positive 30%. And then we also did some noise injection. So some of the images had up to noise of up to 1% of the pixels on the image. And as you can see here, this is what the train test split looked like. We had 5,688 training images, 1,400 valid set images, and then 671 test images. And all of these augmentations were done through the RoboFlow AI. And that is all from me. Thank you.
Next, let's take a look at the model's training metrics. So during training, we monitored 4 key metrics, including box loss, which evaluates how accurately the bounding boxes align with the truth. You can see this in the top right graph. We see a constant decline across all 100 epochs, which shows that we're improving localization accuracy. Next is class loss, which measures how well the model is classifying each object. This also drops steadily, and this is also proof that shows that the model is learning to identify proper categories. Next is the distance focal loss, or commonly referred to as the DFL, and this measure is used to enhance localization precision for smaller overlapping objects, and this can be seen in the bottom right plot, which shows this loss is trending down as well, and it's a good sign that the model is refining or improving in its spatial predictions as well. Lastly, the last metric was precision, which tracks the accuracy of the model's predictions overall, which can be seen in the bottom left graph. You see it improving sharply later on, and then it starts to wiggle around, oscillate a little. This tells us that the model became confident and consistent after the first learning phase around, you can see epoch 18 or epoch 17. Next, once training was complete, we decided to evaluate the model on the validation set. And one of the primary evaluation metrics was the precision confidence curve, which you can see on the plot here. This shows how confident the model is against how precise the predictions are. So the bold blue line here you can see represents the average across all classes, and it achieves almost perfect performance, hitting a maximum precision of 1.00 at 0.994. And we also decided to use the area under the curve as a general performance indicator. Here, AUC, or area under the curve, is 0.965, meaning the model is really, really good at distinguishing between object classes. Lastly, we reported the MAP at 50, which is the mean average precision, which we covered earlier, at an IOU threshold of 50%. And the value here is 0.974, which is really good and shows the model is very effective at detecting and classifying objects at a high level. Overall, these metrics show that the training process was successful and the model generalizes well to unseen data and does not underfit or overfit.
So in order to see how the model is performing, we went ahead and applied it to a validation set. As shown on the right here, this is a randomly selected set of pictures, and I know it's a bit hard to see, but overall the model is able to correctly identifying the signs, boxing them, and identify them with a good level of confidence around 90%, which is relatively well. And here's another image set that shows how it's performing prior to training and after. As you can see before, it's not able to identify some of these signs at all, or it misclassifying this waiting sign as a stop sign with some level of confidence. But then after training, it's able to do substantially better, correctly labeling these signs with a good level of confidence. Even though this one has some less confidence, it's still able to box them correctly. The end goal of the project is still able to predict on a real-world scenario. So we applied the model to this driving scene to see how it's performing. Let's slow this down a bit. See, it's getting the bump sign here. It's getting the knowing sign on some frames. It's the speed sign. It's thinking this as a speed sign. It's not right. Speed sign. It's thinking that's a bump. No, it's. Here it's thinking this max weight sign as a speed limit sign. But that's okay because we didn't quite train it on the weight signs. And it's getting the no weighting sign. So there are still a number of limitations for our model. As you can see from the video, it is not able to identify the signs from a far-away distance. And you can kind of see that the confidence level for the signs that it does identify gets higher as the signs get closer to the screen. Now this is because we simply didn't train it enough on those far away distances pictures, simply because we that would require a much larger data set. In an ideal world, we want it to be able to predict on a more variety of signs, as well as predicting them with some augmentations, but that would substantially increase the size of the training set, as well as the computation time and cost for the model to train on, some of which we are not capable of at the time of this project. But that is definitely something we could improve on in the future if we were given more capacity. Another thing is that we couldn't find a good US US sign dataset, so we are stuck with using a European traffic sign set. That would make our model not applicable to the US market, but even so, it still gave us a good example and a good indication of how the model is performing on a similar environment, which we still definitely learned a lot from in doing this project. But yes, that's just some of the things to keep in mind on for the future as we improved on this model. Here's some of the references that we used. They're also linked on our blog. And that sums up for our project. We thank you so much for your attention, and we'll see you next time.